Test.
هاو
Test, test, test. Test, 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 test. Test.
حاجة دابا مشكلتي في هذه في الضوء مشكل الضوء دابا المشكلة هما
Test, test, test. Test, test.
Oui, oui, voilà. Oui.
Test, test de micro, test. Test, test. Test, 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 test.
Oui. C'est bon? Oui. 1, 2, 3. Pas là? Là. Oui, l'arsène. D'accord.
Exactement. Je préfère un micro je sais pas, il est tout neuf, en plus il est tout neuf et je sais pas pourquoi. Ah oui, exactement. C'est...
Ça y est, tu es prêt? Impeccable. Bon, Kamel dit qu'il faut qu'on attende encore un peu, qu'il y ait plus de monde. On y veut payer.
Également, c'est qu'après, il fait 1 heure.
Chercher Okay, welcome to this first session of the afternoon. I'm very pleased to chair the keynote presentation of Professor Yves Lepage. Yves Lepage got his PhD from JETA in Grenoble. At that time it was the place to be for machine translation, so best place to be. He has been then with the ATR, the famous ATR laboratory in Japan, before becoming professor at Waseda University, one of the most famous universities in Japan. Professor Lepage is member of the Information Processing Society of Japan, of the Japanese Natural Language Processing Association, of the French Natural Language Processing Association, ATALA, and he was the editor-in-chief of the French journal on natural language processing named TAL. Yves, it's up to you.
Thank you very much for the introduction. The first thing I would like to do is to thank deeply the organizers of this conference for inviting me here from Japan. I had a map which was used, which was used in the last days when I visited France. So here it's not written Morocco, Japan, sorry, but French, Japan. Japan is over there if you want to. And I had the suggestion of introducing, in fact, a little bit Waseda University, so I will do that in 2 minutes. Waseda University is a university which is not that old. It's something like 130 years old. It was founded by the way, I've got a picture, by somebody who is called Okuma Shigenobu, who has been twice Prime Minister of Japan at a moment in the history of Japan where it was, I mean, the education of people, as is written here, the enlightenment of people was necessary in order for Japan to walk towards progress. So Waseda University is a university which is known for its faculty of literature, of law. Curiously, it has no faculty of medicine, and a lot of alumni from Waseda University played an important role in the cultural, politic, and also economic life of Japan. In fact, I think that you know the brands Samsung, Sony, all these people, these CEOs are from Waseda University. It's a university which is pretty open to foreign students, so here is the recruitment advertisement minute. If you want for, I don't know if there are students here, but if you want to join our university, you are welcome. Please just come and meet me. Okay, the interesting thing with Waseda University is that it's ranked #1 in Japan for employability, which means that all our students find a job immediately after graduating. So that's a good point. And it's also very good in rugby. Okay. In fact, I've been asked that several times here. And where do I come from? Waseda University has several campuses all over Japan, or well, I should say mainly in Tokyo and outside of Tokyo, and there is another one which is located in the southern part of Japan, and this is where I come from. It's called the Graduate School of Information Production and System. This is a place where we are doing things around vision, intelligent networks, things like that. And so I'm leading a lab which is the name of which is Example-Based Machine Translation, Natural Language Processing Laboratory. So we are doing machine translation, natural language processing, and the particularity or peculiarity is that we are trying to use example-based methods. And what I will present today is something around the creation of resources for Chinese-Japanese machine translation, but we are dealing with other topics like alignment and things like that. And I will make the link during the talk with this technique, which is called proportional analogy. So the title of this talk is Automatic Production of Quasi-Parallel Corpora for Machine Translation. And as you understand, we will speak of or about machine translation, which is a slightly different topic from speech recognition. This work has been done with several students, and I want to name one of them, Yang Wei, who got her PhD thesis during summer. So I will introduce the motivation for this work. Then I will show you how to apply what we propose, and we'll show you how to generate or produce quasi-parallel corpora for machine translation. Then I will show the results of several experiments and conclude. Okay, so the motivation is something which is pretty classical. That is to say, we have languages which are, as we say, well-resourced. And for example, Chinese and Japanese are two well-resourced languages. So there are plenty of corpora, there are term banks, there are dictionaries, you have segmenters for tools, you have morphological analyzers, syntactic parsers, things like that. But if you are concerned with machine translation, astonishingly enough, Chinese-Japanese is a less resourced language pair. There are no freely available corpora with Chinese and Japanese in it. So times change, yes, but if you want to do interesting research and use a certain number of sentence pairs, as we do in machine translation, then there is no data. Except that there were two corpora which have been released, and the situation is not as friendly, if I may say, as with some European languages where you can freely download from the web, especially from I'm speaking about the Europal corpus. You can download from the web as you want, freely, large amounts of data. Here, what we have as a situation is a situation where you have to participate in some evaluation campaigns in order to get data, Chinese, Japanese aligned sentence pairs. So yes, there is data, but you have to participate in campaigns. You have to sign agreements. You have, for example, for the second corpus I mentioned, the Japanese Patent Office corpus, you have to sign an agreement and say that in 1 year, after you use the data, you delete the data from all your computers. Okay, so this is a situation where, which is not the standard one, the one we are used with. Okay, so this is the standard question that people have with less resourced language pairs or less resourced languages. You say, well, I've got a corpus, but it's too small. And so the answer is just, yes, okay, so make it larger. Okay, so how do we do that? So for example, you can say, okay, we have people sit down and we have them write down sentences and translate, for example. So the standard excuse is it's costly. Or you want to create parallel data automatically, but the question is how, so we will see some answers. One of the standard way of doing is to look for comparable data and to extract parallel data from these comparable data. What will happen, I hope, in the future, and it starts being like that. There are two recent papers using neural network approaches, and they claim to do machine translation without a parallel corpus, so relying only on monolingual data. So, well, of course, it doesn't work so well. Well, we are at the beginning of that, but I think that in some years, maybe we will be able to do pretty good systems relying only on monolingual data. Okay, so at the moment we have Chinese, Japanese. there is a lot of monolingual data. There is not so much as for parallel corpus, aligned corpus, so what shall we do? Another question that you may ask when you work, or some years ago, that you could have asked, is linked with the technique which was used to do machine translation. And the technique was statistical machine translation. And in statistical machine translation, you use a parallel corpus, and what you output as a first step is something which is called a translation table. Let's say it's a dictionary. It differs from dictionary in two directions. The first thing is that it's somehow a word-to-word translation, so you put a probability, you associate a probability, you assign a probability to the fact that this word may be translated by another word. And it's not only word to word, it's maybe 2 or 3 words to 2 or 3 words, okay? So that's called a translation table. So what you could do is to say, when we are confronted with the problem that the translation table is too small so that you cannot translate well, so the answer to that is, okay, make it larger, so how? And a proposal, an interesting proposal was to say, okay, you just imagine that you have more small pieces corresponding to small pieces. So there is a very nice word which was introduced for that. You hallucinate translations, okay? So how can you do that? So there was work about that, and the idea is again to use comparable monolingual data. And what you do is that you try to point where the translations are, so that you will imagine that some words correspond to some words. You do something to eliminate the bad candidates, okay, and you increase your phrase table. So there has been work done in this direction by other researchers. We did that too, and our first idea was to use an operation that is called proportional analogy, that I will explain later. But it consists in producing new data relying on old data. And we did some experiments, and okay, we got some improvements in what we call bleu points. So bleu is the standard measure to measure, I dare not say the quality of translation, but the accuracy of translation. Okay, so how good, I mean how close a translation is to the reference translation. The point, well, saying that this is that this reflects quality is subject to debate. Okay, so we did that, and we were able to produce some new phrases in translation tables. So we made the translation table larger, and we got small improvements in situations where we had simulated situations where we had not that big amount of data. Okay. Okay, the main point was that we were using this proportional analogy thing. So what I will present today is going back to the idea of generating parallel sentences, not only small portions of text corresponding to small portion of text, and starting from monolingual data, because we have that for Chinese, we have that for Japanese, and so we will use unrelated monolingual data, and the tool or the operation or the process we will use will be proportional analogy, so that we will create new things from old ones. And then what we will do with standard statistical machine translation is that we will append the new data to the training data we had, and we will see whether we perform better or not. So this kind of work has been published in several papers that I just quote here, sorry. And what I will do is to report on the results published in this work. Okay, so what we want to do is to generate new parallel data And you may start to ask why I use something like quasi-parallel as an adjective for corpora, and I will explain that. But the idea is that what we will do is apply a two-step process. In the first step, what we will do is to create new monolingual data. And in the second step, we will look at what can be said to be translation. I mean, sentences being translation of other sentences in these new monolingual data. Okay, so this is the a theoretical view at how you can do it. Now, whether you do something first and then something after will be a matter of implementing the pipeline. But from the theoretical point of view, we first generate monolingually, we generate data, and then we look at what may be considered as translation in the new data. So this is an ugly picture of what can be done. I really dislike this picture, but we never found a nice way of presenting things. So maybe saying it with words, this is an exception to the standard saying which says that a small picture is better than is worth 1,000 words. But here maybe the explanation in words is better than the ugly picture. So we will have two parts. The first one is generating new monolingual data, and the second part will be to identify the translations in the new data. To generate new monolingual data, what we will do is to construct analogical clusters. And that's an ugly word, so I will need to explain that. And using that, we will, from old sentences, we will create new sentences. There will be a problem if there are linguists in the audience. They listen to the word analogy and immediately, this is a reflex, they say, oh, overgeneration. So we'll have to explain how we eliminate overgeneration, that is to say, how we filter the new sentences so that we retain only the ones which are valid. So let me explain this first part before before we go into the second one. Okay, so I used the word analogical cluster, and this is an example. I hope it's clear for everybody. Okay, it's okay. So even if you don't understand Chinese, and by the way, this is my case. So even if you don't understand Chinese, with some effort, what you can see in this picture is that the small picture here is replaced by this small picture. So what is on the left here, this small thing, is replaced by this other small thing, okay? We call that Hanzi, so Chinese characters. And in fact, if you look at the meaning of these sentences, on the left you have a negative sentence, and on the right you have a positive sentence, okay? By the way, that's the starting of Chinese writing. Okay, these oracles were, will there be a favorable crop next year, or there will not be any crop next year, and well, okay, but that's the starting point of Chinese writing system. Okay, so this is to illustrate an analogical cluster. So an analogical cluster is a set of pairs. Here these are actual sentences. Okay, they are short sentences, but this is actual sentences. And on the left, you have something which differs from what is on the right by, here in this example, only one character. Okay, so you change from the left to the right by changing something. Okay, so here it's a substitution. Here is another example. By the way, what is in blue is to say that one sentence may enter into different analogical clusters. And here the opposition is the fact that on the left we speak in general, but on the right this is the effect, which is whatever. Okay, so it's not a substitution here, it's an insertion from left to right. I add something, okay? And what it is, again, is that, I mean, this is an analogical cluster. Okay, so this is a language I'm more confident with. So this is Japanese, and this example shows you that you can just replace please by I would like. Well, you can do that in any language, by the way, okay? So we did that in Chinese, you can do that in Japanese, and so you get the idea of what analogical clusters are, I hope. Okay, so how do you do that? How do you extract this kind of clusters from standard data? So let's speak about something slightly different, or I give, it's just to show you that we can do that with, well, possibly any kind of object. So let's suppose that we have small matrices of white and black pixels. I represent them as vectors, so the important thing is I represent something as a vector. And in fact, here vectors of integers, okay? So I have different vectors of integers, and what I want to do is to look at situations where one vector is to another vector in the same way as a third vector is to a fourth vector, in the same way as a fifth vector is to a sixth vector, and so on and so on. So in order to do that, we designed specialized algorithms which first were transforming the just the series, the sequence of vectors that we had into some structure, level by level, that we explore in parallel. So this is just an illustration of it. You have the repetition of the same data structure here and here. And we are at level 1, and what we will do is to explore level by level to see whether we find the same differences, okay? And thanks to that, at the end of the execution of this procedure, we are able to say that this has the same value on the 3 levels as this. The 3, we observe the same differences, the same ratio, so that we say that A, this vector A, is to vector B in the same way as vector D is to vector E. So we can say A, B, E, sorry, D, E, okay? And we built a cluster here. Well, it has only 2 lines, 2 ratios, but we were able to build it automatically. Just a remark, the naive way of doing, that is to say, computing all the possible, trying to look for all the possible places where we have A is to B as C is to D, would be n to the 4th in complexity, and this algorithm reduces the problem to something which is just n squared. So it's faster, well, it's faster, it's slow, but okay, reasonably fast, so that on thousands of sentences, you just run that for, I don't know, it depends on the language, by the way, for 30 minutes or 2 hours, and you get automatically the analogical clusters that I've shown before. So if we want to define formally what an analogical cluster is, we would say that it's lines, I mean rows of ratios, and it's defined formally by the fact that we have the first vector is to the second vector, as the third vector is to the fourth vector. We define this using a representation which is near to a vector representation of sentences. In fact, we just count the number of letters or characters we have in sentences, okay? So that's pretty easy to do. The next thing which is not that easy to do is, because of the definition which was derived from further research, is to add a constraint on the distances between the sentences or the sentences or the strings of characters that you have. And to measure that, we use some particular edit distance. Okay, so for example, here is our 4 sentences in Japanese, and we check that for each different character, we see that the difference for the number of characters, this one, here in this sentence minus this one is equal to the number of characters, this one, that we find here, minus the number of characters, this character we find here. So 1 minus 1 equals trivially to 0 minus 0, so the constraint is met, and so we can carry on. Then we check distances. Okay, so this is implementation, but what I want to convince you of is that it's possible to do that automatically. I hope you believe me. And so we are releasing these tools. By the way, if you are interested, you just type in, you Google, as you say, you just Google Lepage-lab words to grids or words to clusters, and you find the page so that you can download the tools that we released. Okay, so what I've shown is how you can construct automatically analogical clusters from data. So you imagine easily that we can do that in Chinese, we can do that in Japanese. Of course, the probability, if I may say, or the possibility of extracting clusters may depend on the length of the sentences, right? So it's supposedly and practically, it works better with shorter sentences. And then what we want to do is to use these analogical clusters to create new sentences. So how will we do that? It's pretty easy to understand. Let's suppose I have an analogical cluster here in Chinese, and what I see is that I replace these 2 characters with, I substitute them with these 3 other characters. So if I have something like that as input, I input that into the analogical cluster. Somehow, what I may get is, okay, the transformation where I will have these 2 new sentences. In Japanese, what I will do is to replace this with this and this. So this shows you that it may be more complicated than just one substitution, okay? But the result of that is that with an input, we get some output, and this may be new. Well, it's the fact that doing that with a lot of sentences and a lot of clusters, we get a lot of new sentences. And I will show you numbers which are pretty impressive. Sorry. So, to summarize the picture again, what we had, or the main operation that we relied on in order to create clusters, analogical clusters, was the notion of analogy. So between 4 strings, we have a relationship. And to produce new sentences, what we use is the notion of an analogical equation. We solve these analogical equations so that we get new sentences. Okay? So here is the same example, and here is 1 line from a cluster. Here is a sentence that I got from some data, and what I'm able to do is to produce a new sentence. Okay. And again, we released these tools, so if you are interested in testing them, and well, we are interested in hearing about the bugs, but we released these tools so that you can use them. Okay, so you understand that we were able to structure data monolingually. If we use old sentences and we somehow input them into these clusters, we get new sentences. And now the problem is that, as you may imagine, there may be problem. The characters are not in the right order. It doesn't make sense. This is what we call overgeneration. So we need to filter the sentences which are output by this technique. And this is what I want to very briefly describe. What we did was to use, well, no, here I don't write it, but we tried plenty of techniques. So of course language models, SVM techniques in order to make the difference between sentences which are valid and sentences which are not valid. Well, after all, this is the problem of okay, grammaticality or checking a sentence for grammaticality, so nobody has the answer. But there is an old technique which consists in when you have a string of words or characters to look at a window of sequences of words or sequences of characters and to check whether this small piece belongs to an existing corpus or not. And astonishingly enough, this works very well. So we are not the only one to use this technique. It's not a very well-known technique, but it's pretty efficient. And so we use it for filtering. We also try to use the BLEU score, so the score which looks for the accuracy of translations of machine translation systems. And so the idea is, let's say we want to maximize some BLEU scores of the new sentences that we generated against some corpus. How to measure that? Sorry, I will skip this slide because this is what I explained. Maybe I will. And for BLEU scores, I don't know whether you are familiar with this, with the BLEU measure, but the idea is to compute some geometric mean of the number of engrams that you have in a reference corpus, reference document, or even only a reference sentence, so that you get a score, and this gives you an idea of how close you are to some ground truth or gold standard or reference. It's not so easy to apply this idea to the problem we have at hand, because it differs from the standard configuration where you have some sentence and you want to check it against another sentence. Here we don't really know what we expect. So what we decided to do is to group the sentences we start from in small, so I don't want to say clusters, but groups, to group them by similarity and to compute the quality against these groups of sentences to calculate the BLEU score. And then we rank the sentences according to the BLEU scores, and then, okay, what do we do? Threshold, we didn't know exactly. It's not that, well, I will say a word afterwards. It's not that great, but okay, that's something which we can imagine because we are people working in machine translation and familiar with BLEU. Okay. Okay, so using these filtering methods, what you can do is, in the case you have plenty of different sentences, well, it may happen that you eliminate some of them and you keep the ones which are supposedly grammatical and meaningful. And I will show you numbers to show you what we can do. Okay, so this is creating new monolingual data, and the problem is then to spot which of the sentences we have in the monolingually generated data are translations of one another. So in order to do that, we rely on two ideas. The first one is that what we will use as a starting point, and in fact this was illustrated, sorry, this is illustrated here. What we will start with is with sentences which we know in advance are aligned, okay? So that supposedly, if the transformations we apply are the same, supposedly this should be a translation of this. So in order to know whether the transformation which is applied in Chinese is the same as the transformation which is applied in Japanese is the same, we need to check for the similarity of the analogical clusters. So for that, well, this is a slide to make very clear what I want to explain. On the left you have Chinese, on the right you have Japanese. We have clusters which have been output from monolingual data. So they are unrelated. So the sentences are unrelated. These are not translations, well, some sentences may be translations of one another, but this is not in general the case that it is like that. And so what we do is that we generate clusters in Chinese, we generate clusters in Japanese, and it may be the case that the transformation between the left and the right in both languages is the same. So I want to illustrate that with sentences in English here, and to make very clear the fact that here these sentences are not translations of these ones. Okay? And these sentences are not translations of these ones. But we have the fact that the transformation from the left to the right is the same. So here I illustrate only with English, and you suppose that it's Chinese or you suppose that it's Japanese. But what we have is that we have the same transformation. Okay? So we want to spot the same transformations in the analogical clusters we generated. How can you do that? So the idea is to use standard similarity techniques. We first extract what is different on the left and on the right. So written with notations, this gives you this. And we do that in words. Okay. We have segmenters for Chinese, segmenters for Japanese. There is no space in the Chinese, neither in the Japanese writing system. So we get the set of words on the left, which will be replaced by a set of words on the right. And what we do is just to compute the dice coefficient between what we have on the left and what we have on the right. Okay. In each language, we take the average, okay, and that's done. We could have used something else. Well, we decided to use that. This gives us, for each pair of clusters, this gives us a score for how confident we may be that one cluster corresponds to another cluster. Okay, so here is, for example, the illustration on the previous pair of clusters, and we would say that okay, the similarity is 0.8333. Okay, when we have done that, what we can simply do is to start with translations. We apply the transformation in Chinese and Japanese in parallel. We get new sentences, we filter, so we get this sentence and this sentence. And as a result, if the two clusters have a score of 0.833, we will say that these two sentences, well, should be considered as, well, maybe translations. But the maybe is the question. So we will not say that these are parallel sentences. We say they are quasi-parallel sentences, quasi-translation, okay, or quasi in American English. Okay, so this is the presentation of what we can do with the technique we propose. We are able to generate data. So let's have a look at some experiments. And I'm afraid that I will run out of time, so I will run out of the experiments, and that's that's good because these slides are terrible. Okay, so I present some results that we obtained in different well, that we reported in different papers. And when I say the slides are terrible, this is because this is this kind of slides. It's just numbers. You you don't understand anything. No. What we should have a look at is what I call the number, so the number of clusters we are able to produce. So here is an example where we start with, this is megabytes, not the number of characters, not the number. Oh, you may divide by 2 and you have a pretty good idea of what it would be in Chinese or Japanese, well, 2 or 3. But you get millions of clusters. Okay? It's amazing. Well, the sentences are short. Okay, you get a lot of examples. A lot of clusters are very short, only 2 lines. Okay? But it's amazing how many we get. Except that when you try to look for the similarity, you reduce the number drastically. For example, if you take similarity over 0.5, only 400 are, comparable clusters. Okay, the other thing we have to look at is that with the training data that we will use to train our machine translation system is this number. So the sentences are pretty short. The new sentences that we were able to produce is only 10,000, okay? So if we run experiments, SMT, standard SMT experiments, so this is what I call the baseline, we get this blue score, which is a reasonable blue score for Chinese, Japanese. And if we add the quasi-parallel sentences, we observe a jump. And this jump is not negligible. It's pretty good. It's, well, of course, statistically significant, but okay, 2 is, well, 2 or 1.5 is not that bad. The other one in Japanese Chinese is pretty good. And so this was the first experiment that we ran, so we thought that the technique was promising. So we carried on. So we did more experiments. So we used parallel data in a number which is something like 110,000 parallel sentences. Of course, we examined different ways of filtering. By the way, as usual, a combination of 2 methods delivers better results, no surprise. But here, the improvement in scores are, frankly speaking, amazing. Well, except when we went from SMT to NMT, did we observe jumps in blue scores of, I don't know, 6, 7, or now 10, okay? But here we have something like 7 points improvements. Okay, the important point here is the number of quasi-parallel sentences that we got relatively to the number of sentences we started from, okay? And here we really add an enormous amount of quasi-parallel sentences relatively to the training corpus. Okay, I will skip the analysis of the data. What we did in the middle was to look at, by hand, okay, to look at the quality of the generated sentences. Okay, 1 sentence out of 5 or 1 sentence out of 2 is correct. And the filtering methods that we apply are really very efficient. We can reach 99% correctness, but we throw a lot out of the window. That is to say, precision is very high, recall is terrible. Okay, and so what we looked is the influence of our technique on this core dictionary that is used in statistical machine translation, that is to say the translation tables. And what we have is that, yes, really we add new entries in the translation tables, and it's not really on word to word, unigram to unigram that there is an increase, but the favorable ones which are around here, okay? And so here at the bottom of the slide you see additional, for the same Chinese phrase, you see what is added in the translation table and all these new phrases in Japanese are in fact valid ways of saying the same thing. And I make a remark. There is no new word introduced. Okay, we finished with, we participated in this evaluation campaign where you get some data that you have to promise to delete after 1 year, or that you have to, well, for which you have to sign a new agreement each year. And so this is the what evaluation campaign, and we use data which is called ASPEC. What we had is disappointing results. We got improvements, but pretty small improvements. By the way, we observed a reasonable improvement when we used Moses 1.0, so which is the name of the standard tool with which you used to develop statistical machine translation. And I can tell you that there was improvement from version 1.0 to version 2.11 to our not in favor of what we did, because what we observe is that we don't get any fantastic further improvement with our method using this new version of the statistical machine translation standard development tool. Okay. Okay, so I mentioned the fact that I presented it somehow from a theoretical point of view. You can work on the pipeline to do everything. Well, for example, at some point in time, we were able to really speed up everything. So it took 3 hours to do something, and by using some standard computer science techniques, we were able to reduce to 1 minute, so we are pretty happy. And this means that, in fact, it's not that costly in time. Okay. Okay, so I will skip this. This is my last slide. It is a synthesis of all the experiments that we have done in numbers. And what I want to do is to leave that somehow open, but I just want to make some remarks. So here, this first experiment is an experiment where we got pretty high improvements. And what we used for training data is something which is subtitles, so it's pretty diverse sentences. The additional data is the additional data is generated from clusters which are built from data which is different. So web news, okay? And what happens here is that we add, relatively to the training data, we are able to add a lot of new quasi-parallel sentences. This is not the case here, where we were not able, so this is the deceptive, I wanted my students to run deceptive experiments. These experiments, we show that it doesn't work. So this is the case, we use the same corpus everywhere, okay? And so the idea is that, yes, of course, if you don't introduce any novelty in the, either from the clusters or from the seed sentences, then you will not observe anything. Okay, so this is what we observe. What is the status of such an experiment in science? But okay, it shows you that, okay, it meets somehow intuition. So in the middle, with other experiments, so what the observations that we made was that, okay, you can get some improvements, but the important thing is not the fact that the sentences are well aligned. Much more important is the fact that the sentences are grammatical. Okay, so there is a surprising fact that you may think that, oh, the fact that it's true translations, that they are true, that these new sentence pairs are true translations, is the core of the key point in the technique. And no, it seems it's not the fact, what is more important is the grammaticality of the sentences. So if the quality of the sentences is not that great, you don't get a lot of improvement. Okay, so to summarize, what I've shown you is that we can follow an original path to add new training data to improve the performance of phrase-based statistical machine translation. What we did was to add new data, which is not that well aligned. Well, it's well aligned, but not really translations in all the cases. And okay, in some experiments, we were able to get improvements. So the problem is to explain exactly what happened when we performed these kind of experiments, and what I claim, but it somehow remains to show, is that what we did was to produce small variations, and this is what we see in the translation tables. We add variations in the way you can translate, okay, the same, well, let's say for the same Chinese phrase, how you can translate it into Japanese, with more variations. So I think that this is the key to the technique, because afterwards, after everything, well, I mean, or rather simultaneously, when you produce candidate translations, what you do is what is important is the target language model. And I think this allows you to have more translation candidates which are more reliable from the point of view of the target language. So this is what I've just said. These small translations, these small variations are seen in the translation table. And so this is what you may encounter in the test set too, from the point of view of the source language, so that, okay, maybe it's better translated. I mentioned the fact that the grammatical quality seem to be more important than the fact that the sentences are well aligned. So this is what, I mean, the future of this. The last line is the only one which counts, in fact. No, there is engineering effort to put in speeding up everything. We have from the, what shall I say, well, scientific point of view, I would like to better identify the kind of variations that we introduce, because I think this is an important point. So at some point in time we were criticized, and somebody raised his hand and said, well, you just introduced new words out of vocabulary words. No, we checked for that, and no, it seems it's not really the case. Okay? Yeah, they are. But it's not only that. And so we would like to reproduce these experiments not for different language pairs. So Chinese, Japanese was the right case to select, because it's true that it's, as a language pair, it's less resourced language pair. And of course, I say the last line is the most important one. So everybody has shifted to NMT, so we are shifting to NMT too, of course. And there are some talks this afternoon which raise the question of knowing whether statistical machine translation is dead. I'm very sorry to say that I think it's the case. So that we have to do that for NMT. Okay. So I want to acknowledge grants from Japan. We got money to do these experiments. And of course, I want to mention all the students who worked hard in running all these experiments, and especially Yang Wei, my former PhD thesis. So thank you very much.
Thank you very much. It's very complicated to say thank you for listening in Japanese.
Politeness, Japanese.
Could you say it? Could you say it?
ご清聴ありがとうございました。
Questions? Yeah, but you.
So, hi everybody. Thank you for your interesting talk. I have a question concerning your method that you have used in order to filter your generated sentences. I didn't understand how you have used the blue scores in order to to filter the sentences. I mean, what was your reference, and could you repeat this? Yeah, thank you.
Exactly. So this is the point. What is the reference? Right? We don't have a reference here. So how do you? So we don't use the blue score as telling us that something is the right answer against some reference. What we did was to group sentences. Okay. So you know that there is a way of using blue scores, which is the blue document score. And so what we do is that we check for these n-grams, whether, in fact, it's pretty similar to the other technique, right? We look for the existence of the n-grams in the references, except that here with the blue score, we compute some strange formula, which is the geometrical mean over n-grams from 1 to 4. Okay, so it's different in this way from the other technique, but basically we check against a reference. Here the reference is not the entire corpus. In the n-sequence filtering method, the reference is the entire monolingual data that we have, except, so here, because for the blue score, you have to have a limit in the reference, right, somehow. So here we limit ourselves to a number of sentences which are, we know in advance, similar to what we output with during generation.
I had a question about the filtering also. You said that one of the possible explanations for the small results that you got at the end was the fact that after filtering, you have your filter has such a low recall rate, very high precision but very low recall. You also made a comment at the end that grammaticality of the analogies seems to be more important than there being exact translation pairs. So this, I wonder, have you considered the possibility of using a monolingual parser? Certainly, these are both well-resourced languages monolingually, so there are parsers that exist for Chinese and also for Japanese. Could you use a parser to check the grammaticality of the sentences explicitly?
Yeah, you're right, yeah. How comes we didn't? we are too data-oriented people, and yes, but that's true. Yeah, we could have used that. Yeah, there are parsers. Yeah, there are parsers. Yeah.
Thank you. Good talk. So you talked about the blue score. That's great. Did you consider other metrics like TER or Echter, where the quality maybe?
Okay.
Okay.
Yeah. This blue technique itself as a filtering method didn't work that well. Okay, the n-sequence filtering method is more efficient. Okay, and so this is why we didn't want to spend a lot of time in looking for that, because it doesn't perform that great. It adds something when we combine it with the n-sequence filtering method, but no, really the n-sequence filtering method is more efficient. So, but yeah, okay. As I just explained, there is a link between the two methods, which is to check for the existence of these n-grams, right? And so would you see that in other, I don't know.
What I have in mind is mostly the HTR, where the H stands for human, where you have a better reference, and then can play a role on this situation.
Thank you very much. You know that I like too much this analogy method I discovered by reading your papers 10 years ago. And something you have not said here, but maybe for the people who are here have not remarked something. Today, everything is using word-to-vec, the embedding methods. And the embedding methods, everyone today discovered the analogy between king and queen, between man and woman. And that is what you did in this work. So this is something which is very important to say. This was my remark, but the question was, I have several questions, but maybe I will discuss with you another. Yes. My question is, have you done experiments by introducing more and more new parallel fragments, because you have errors in your fragments, and maybe the curve of the original corpus with the new one can cross each other, and maybe your results will be worse. Have you done this?
No, that's a good idea. Yeah. Thank you. Yeah, that's a good idea. Yeah, to have a look at that. Yeah, the not learning curve, but wow, cool. Improvement curve.
Question for Khalid.
It's going to be a very quick question because not my field. I'm very surprised that so ancient cultures and neighbors, and they don't have large parallel corpora. Is there any fundamental cultural or technical reason for that? Do you have an answer to that?
I tell you a story. So some years ago, the political relationships between Japan and China were pretty nice. And so on both sides of the sea, it was decided to have a common machine translation project, okay? And then the political relations went not so okay. And so nowadays we have 2 machine translation projects in China and in Japan. Of course, people are collaborating, of course, but no, it's not the same money shared by both countries. No, it's separate. But of course, we know the other researchers in China. But so that's it, okay.
So I guess the solution could come from private companies. For if Sony decides that it's worth it, but then we will be unhappy because all your work will be no.
Okay, so here you make the point. Private companies, they have data.
Ah, so they have.
We don't have as researchers. That's all. Yeah.
Okay, thank you.
Any other question? No. Okay. Thank you very much. It was very interesting.
Yes, you can start. Thank you.
Several approaches have been proposed in order to
idea of the plan of the Japanese natural language processing system?
Dictionary in the normal machine translation system. We improve a little bit the blue by 0.4%. Now, concerning the translation of infrequent words, so there is an interesting consequently the performance of our system. The before last test concerned the architecture of our normal machine translation system. The last test concerned the tuning of the parameter of the beam search. So as I explained before, the beam search explored in each level a set of best translations. So the size of this set represents the beam size. In all the previous experiments, the beam size was fixed to 1. So this means that only the best translation is considered in each level. So in this test, we vary the beam size from 2 to 15. But by increasing the beam size, there is another problem. The normal machine translation will generate short sentences, because remember that the target probability generated by the neural network is the product of the probability of each word given the history of this word. So longer the sentence, smaller the probability. So in order to handle this problem, we can use a word penalty, where the exponential of the word penalty will be multiplied by each probability generated by the neural network. I mean this probability. So if we fix, for example, the word penalty to 0, this means that this probability of each word, given the history of this word, will be multiplied by exponential of 0, which is equal to 1. And in this case, the probability generated by the neural network will be not altered. So by varying the beam size and the word penalty, we achieve the best performance by using a beam size of 15 and the word penalty of 0.5. And with this configuration, the blue achieved on the test was 24.37, which is so close to the result obtained by the statistical machine translation system. So, as a conclusion, in this work, I presented the new paradigm of machine translation based on neural network. This model is considered as an end-to-end model, which means that all the latent structure that is used in the statistical machine translation are implicitly modeled by a single and a large neural network. But as we saw through the different experiments, the neural machine translation system, baseline system, needs always an external component and sophisticated architecture in order to achieve state-of-the-art results on constraint, we can say corpus, because we use a small data set. So, for example, we start from a baseline system where the gap between the two approaches was 90%, and by modifying the architecture and using some external components, we decrease the gap to 0.17. So, as future work, we are working to propose an architecture that combines the two approaches and take benefits from the two systems. And we have to work on the tuning of the parameter of the neural network, because as you know, in the neural network, there are a lot of parameters needs to be estimated. For example, in all the previous experiments, I didn't talk about the learning rate, about the activation function, etc. So we have to fine-tune all these parameters, and of course we need to compare the two approaches on a large data set. Thank you.